So we know that there are a few important features, right? So these are states, first of all, they are discrete, okay, normalized, okay, and they actually form a complete orthonormal set, okay. And also we know the number of nodes, okay, is 0, 1, 2, increase one by one, okay. Right, so these are the important features, okay. And also we know that they are even order parity if Vx equals to V minus X, okay. If the potential has some symmetry, has this refraction symmetry, the states should also be even order alternatively from the first state to the second state and so on and so forth, okay. These are the general features we have learned about this one-dimensional states, and also they are real functions, right? So psi x complex conjugate equals to psi x, okay. Okay. Right. So these are the features we have learned about this 1D bound states, and the reason that they are discrete is actually because we have the boundary conditions, okay. So that's the same. That's why we have this one. So because we have this kind of boundary conditions. Right. So we have first this psi goes to 0 at x equals to plus or minus infinity. So this gives us two equations, right? And also we have at any point at xi, okay, you should have xi minus 0 equals to psi xi plus 0. So this is the one condition. Another one is the differential of this one is also continuous. Okay, so this gives you two equations. And suppose we divided the potential into, say, if I have such kind of potential, so we can divide this one into different regions. Okay, so this is x1, x2, this is xi. Okay, so altogether you can see that at each section, okay, you have a psi x can be written as ai eiki x plus bi eiki x. Okay, so you have 2I plus 2 coefficients, right? But this one gives us 2I plus 2 equations. Okay, so that means you can write down this one as a matrix form. A0, B0, A1, B1, until you have a BI, right? So this is a 2I plus 2 times 2I plus 2 matrix. Okay, so you have this one equal to 0, okay? So these are the equations can be written like this one. So the only way that you have non-zero, the psi should not be 0, will lead to the conclusion that this matrix must be singular. So that means its determinant must be 0. So this gives us, discrete solutions of EM, right? And once you know these eigenvalues of this EM, you can obtain these coefficients, okay, up to a global factor. Okay, so these are the states the general property and the general methods for obtaining the eigenstates and the eigenvalues, eigenfunctions and eigenvalues of the 1D bounded states, right? And of course, we have studied, in details a few cases. For this infinite potential, we know that this is the ground state, and the wave function is like this one, right? So this is E1 that equals to chi squared h bar squared over 2m and w squared, and the wave function is square 2 over w sine, pi x over w, right? So that you have this kind of standing wave, and then the second state is all the function, has all the parity. Okay, so this E2 equals to 2 squared times E1 actually, and the wave function is going to be 2 pi x over w. Okay, right? And you can have E3 that equal to 3 squared times E1. Okay, and this will be the sine function 3 pi times x over w, right? So this function goes like this one. So you can count the number of nodes, right? So you can see that the first state has 0 nodes, and the second state has 1 node, and the third state has three nodes, and so on and so forth. Okay. So this one are the states for the infinite quantum well. So this goes to infinite. Okay. But you can also consider the case that if you have a case that's not infinite. Okay, we know that there is at least one state. Suppose this is the energy that is corresponding to the energy, the first state of the energy in the infinite quantum well, and then the real energy of this one will be slightly lower than this, because the states cannot have some chance to penetrate into the barrier. Okay, right. So this is the tunneling. Okay, so then this k inside this one, you're gonna have the k actually is less than pi over w, right? So that leads to this E1 is less than the E1 in the infinite quantum well. Okay, and of course you could have the second state is antisymmetric again, right? And this one, of course, is also less than the states of the the infinite quantum well. And then you know that if the third state is above this one, and then you have at the most you have only 2 states. Okay, so basically you need just to count whether this energy, okay, so that if this energy, this EM infinite is greater than the V0, so this is V0, okay, and then the number of states okay, and this one is greater than EM minus 1 infinite. The number of states will be just M minus 1, okay? Right, so it's very easy to count the number of states. You can always find a solution, using the graphical method, right? Okay. All right, so that's the general feature we have learned about this infinite quantum well and this finite quantum well. Option material, okay? Is so if we have, for example, a double quantum well, and then we know that there will be a bound state. and there will be anti-bonded state. And the bonded state is symmetric. Okay, the anti-bonded state is actually. Let me use different color. Okay, so that you can distinguish them. Okay, right. So this one is the bond energy. Okay, so you have symmetric states that have the wave function shared by two quantum well. Okay, and if it's anti-bonded states, and then you have the two, like the electron is more separated. Okay, right. We also learned the concept of quantum tunneling. Right. So if we initially have a superposition of these two states, the bonded and anti-bonded states, and then the quantum, the electron will be, the particle will be mostly confined initially in the left quantum well, and then by time evolution, okay, you're going to have you know, the particle turning into the second quantum well, okay, the right one. Okay. Right, because of the constructive and the destructive interference. Okay, so these are the a brief summary of what I have learned about this bonded states. Okay, and now we're going to also discuss a little bit about the scattering state. So what if the energy is above the barrier? Okay, right. So in general, suppose you have so let's consider the case that you have energy above the barrier. Suppose you have something like this one in general, okay? Okay. So what if you have a state like this one? Okay. So then you ask the question, percent E equals to what? Okay. And actually, we can show that for all the energies above this, okay, you find that this actually all these eigen values for E above V0. Suppose this is V0. Actually form a continuum. So that means all E above V0 can be an eigenvalue. Okay. So there's no constraint on the eigenvalues, unlike the case that we had for bonded state. The reason is that in this case, the reason is because percent does not go to 0 at x goes to plus or minus infinity. So that means the number of equations will be less of the number of the coefficients if you divide the space into different regions and you connect them. Okay, so that means you have more coefficients than the number of equations. So according to mathematics, you know that if you have the number of equations less than that, there's always a singular, right? So there's always a solution. Okay, so that means all possible eigenvalues can be, all values above V0 can be eigenvalue. Okay, so these are general remarks. Probably it's too abstract. So let us start with some very simple examples. Okay, right. Let's start with this extremely simple example. V just equal to 0. So this is trivial, right? Hamiltonian is simply just p squared over 2m, okay, plus v, that equals to p squared over 2m. Okay? And so this is the case for the scattering okay, it's actually not really scattering of a free particle. Okay, you know that if you have a wave packet like this one, so this will just go all the way, right, from left to right. Okay, so there's actually no scattering, so the particle will just move them. Okay, but to understand these scattering cases, okay, so this is propagation. So we are trying to figure out what are the eigenstates of this system. Okay, so you know that if we want to solve this problem, we just found that this percent Ex that equals to E percent X, right? And then the solution of this one has been obtained. Okay, so there are two possible solutions, two special solutions. That is EIKX and E minus IKX. Okay, with K squared. Sorry. So there are two special solutions. Of course, with this K equals to 2m E over h bar squared. Okay, so that's a positive number. Okay, so we take this one as a positive number. And so, and then a general solution is also known. Okay, so that is percent E X that can be written as a linear combination of this one. Right. So these are the solutions of eigenstates of this one with eigenenergy E. Okay, they are nothing but just plane waves. Okay. Right. This is already known. Okay, it's a very simple example. Okay. Another. Let's compare this one to the bounded states. So one feature of this one is that you can see that EIKX or E minus IKX, these are plane waves, right? So they cannot be normalized. But we know that any wave function, but we know that Pxt should equal to percent xt percent xt, right? It's just a probability distribution, right? It's a probability density distribution. Okay. So we should have Pxt dx that equals to 1, right? Okay. So that means immediately you got a very frustrating conclusion. So this eigenstates, let's call this one plus minus k, that equals to ikx or plus or minus, can not be a physical state. That's very annoying, right? You found the eigenstates of a system, but this state cannot be a physical state because it cannot be normalized, right? And then you can ask, there was a point of finding this eigenstates, okay? But actually, so the physical state, to make this one, so to make a normalizable state, so we have to form a wave packet. Like for example, you can have percent x t that equals to, the integration of right. right? And then of course there is energy right here. So this gives us the wave packet, and this way, okay, we can actually, for example, you can have a Gaussian wave packet, right? So for example, you can have this k just equals to e to minus k minus k0 squared over 2 sigma squared, right? So this just gives us a wave packet centered as okay. So this is k0, and this is the distribution of this k, right? And with a weight given by 2 sigma, okay, roughly, okay. So that this will give us a Gaussian wave packet, right? Okay. Right. Okay. So this is the point of this one is that the plane waves cannot be physical states. Okay. And the physical states must be a wave packet. Okay. And more importantly, interestingly, you know that because this energy Ek has a distribution, right? Right. So that means this phase factor actually will change with time. Okay. So you can write down this percent xt actually written as something like a percent tiered kt eikx dk over square root of 2 pi, with this percent tiered k equals to just percent k times not time dependent factor, right? So you can see that now this will become time dependent. So the interference will lead to this propagation, the wave packet of this one. So then you have this wave packet actually will, this is a percent x at t equals 0, for example. And then it's going to propagate to another position, okay? Right. So this to the propagation. The interference between different k component now will be different because this amplitude depends on the time. So that means at different time, so you're going to have different positions that have interference that's constructive, and other positions you're going to have interference to be destructive, right? So with the velocity, Vg, that's just equal to partial k at k equal to k0, right? So this is what we have learned about this superposition of many plane waves to make a wave packet, right? And the Gaussian wave packet is just one of the example, okay? In the K space. So in the K space, actually the phi k does not change. Okay. In the real space, this wave packet is moving. Okay. You can say in the K space, you actually have probability distribution is fixed. Okay. So that's a good point. Okay. Let me make a note like this one. So there's a question. This is K is in the K space. Okay, and you can say that percent tiered, okay. And the question is that yes, and actually, if you look at the probability in the K space, that equals to percent tiered K and percent tiered Okay, right? If you look at time dependence, you find that this one actually equals to percent T at K times e to minus ek T over h bar, modulus squared, right? And this one equals to P K0. Okay, so if I have a superposition of this different K component to make a wave packet, so actually you can see that, so this is, let me plot this probability, okay, as a function of time, okay, it's fixed. But in the real space, so this is Px at t equals 0, okay, and this is going to propagate to a new position. Way back drawing. Okay, whatever, you know what I mean, right? Right, so the wave packet actually, if you look at the probability distribution, you have the probability distribution in the K space actually is not changing with time, okay? But because of interference, because the phase factors are changing, so you can see that the interference release the wave packet in the real space is moving, from one position to another position, okay? So is this K the same as the K we have encountered in the bound states? Actually, it's if you only consider PHYS, yes, but now this applies to the whole space, okay? So in the bound states, we only consider a piecewise, region. In that region, you can have well-defined K. But then, if you consider the whole space, actually you don't have a well-defined K, okay? So there is no single K that satisfies the whole region. Okay? So you have to connect them piece by piece. Okay? But in this free particle case, you have the K is the same for all the regions. Okay? So that's different. Okay, so now let's say that we have seen that the physical state must be a moving wave packet. Okay, and you know that you can have this K can be written as can be equal to something that's centered at this K0, and with the weight this sigma, right? And now if this sigma goes to 0, actually, and this percent, this x actually goes to almost like a EIK0x, right? So you can see this one, if this goes to 0, you can have this one to be, a very broad plane wave, okay? So it's this is the M, so you can have something also like this one. So this will be better and better defined, okay, with the wavelength, with the wave vector approach to K0, okay, right. So if this is finite, you can have something like this one, okay. So but anyway, so the plane wave is the limiting case of a wave packet. Okay, centered at K0. Okay, so this one is momentum with energy with momentum h bar K0. Okay, so this one is a limiting case of a wave packet. Okay, that means percent K minus K0 with sigma goes to 0, right? Right. So you can imagine that you can to have a physical set, you must have a wave packet, but then you make this wave packet to be narrower and narrower in the K space, And then this real space wave packet will be more and more like a plane wave, okay, with this momentum h bar k0. But that can never be, realized in, the limited case is the limited case, right? So it cannot be realized in physical systems. But you can approach it, okay, arbitrarily close to it, and then until you have enough, precision, okay. Right. And now let's look at the physical meaning of the eigenstates. Let's write down this one again. Psi E in general of this one, eigenstate equals to A d I kx plus B d minus I kx. Okay. And this one, of course, evolution has evolution with this time dependent phase factor, right? We know that this is not a physical state. And to have a physical state, so this is eigenstate. Okay, and it's non-physical. Okay, let's consider wave packet. Okay, we consider wave packet xt. So that way equals to, say, assume we have a superposition of different, let's say q minus, let's k minus k0. Okay, so we have a wave packet like this one, and then psi e, of course this is a function of k, right, xt, and do this integration. Okay, so this is a wave packet. Okay, it's physical because it can be normalized. So what will be the result? So you just need to put this one into this one to check. So this will be, you're going to have two terms. One is A psi tiered k minus k0 e I k x dk over square root of 2 pi, right? And you have another term. This is B, the integration of psi tiered k minus k0 e minus I kx. It's a minus sign, right? And dk over square root of 2 pi. But of course, you can change the variables a little bit. You can put this one to be change the variable, change it to be plus, and then change it to be minus. That's the same, right? Okay. So what is this one? This is something that we have to know that. So this is a wave packet. Okay, that propagate. This is t equal to minus t, for example. This is e equal to plus t. And what about this term? What about this term? And this you can see that the psi tiered minus k0 now is going to have a distribution at minus k0, right? And this one, this is a psi tiered k minus k0 at the, the weight, the center is the weight is centered at k0. So you can say that that means this is a wave packet propagated from the right to the left. So you're going to have to be symmetrically propagate to this one. Okay, so this is t equal to minus t. This is t equal to plus t. Okay, so basically, now you can see that if you have an eigenstate like this one, and use this one to form a wave packet, you can have two wave packets actually. One is propagating from the left to the right. Another one is propagating from the right to the left with the opposite velocity with amplitude to be A and B. Okay. So let me summarize this one. Okay. So psi ek equals to A e I kx plus B e to minus I kx. Okay. and times this time dependent. Okay. This one is the limiting case of the foreign wave packet. Okay. So you actually have two. You have two wave packets. One is this is A. Okay. So a wave packet. So this is proportional to A. Okay. And goes with the velocity Vg equals to partial E partial K at K0. Okay. And let me put the K0 right here. Okay. And then you have another one. This one actually is at a symmetrical position with amplitude B and not propagating with the velocity that's minus G, Vg equals to minus partial E partial K at K0. Okay. So you have a two-way packet in the beginning, propagating from one from left to the center, another from right to the center. So this is the center, x to 0. Okay, so that's for t. For t equals to to the remote past. We call this one remote past. Okay, that means very early in the history. So you're gonna have two particles, or sorry, two wave packets propagating from left and from right to the center. And then, of course, at t approach to 0, okay, and these two wave packets actually will meet each other. So you're gonna have something like this one. So one goes like this, it's almost arrived like right here, right? And then the other one, so this one is something like this one, okay? So one is propagating to the right, one is propagating to the left. They meet each other, okay? And they actually will, just like two waves, they are propagating through each other without the interference, okay? Without the, but then of course the shape, if we really look at the shape of this one, that will be something like this one. Right. So this is a wave packet, but now it's separating. One is moving to right, one is moving to left, and then of course, and then in the future, okay, for t equals to t, this is much less than -1. This is much greater than +1. Okay, so we call this one remote future. Okay, so after a long time. Okay, so you're gonna have this particle, this wave packet, now it's right here. It's moving still to the right, okay, with amplitude A. And then another one is already, it's arrived in the opposite direction. Okay, so this is with amplitude B. Okay, so that is the physicals. So the eigenstates actually written like this form. So this is eigenstates. It's not a physical state, but it's a limiting case of the wave packets propagating. And it has two components. So A is the forwarding wave amplitude. And B is the backwarding wave amplitude. Right. Okay. And there's one thing that I want to stress. Okay. There's something that's important you should notice. Okay. this is not two particles. Okay. Instead, it is one particle. In superposition of two wave packets. Okay, so this is something that you need to understand. It's not a two particles. Okay, it's one particle, but with one possibility moving from left to right, with another possibility moving from right to the left. Okay, so it has a superposition of two wave packets. Because this is a wave function, so you have two possibilities. One has amplitude A, another has amplitude B. Okay, and A and B are the probability amplitudes. Okay. All right. So that is the. This of course is a trivial case. So we just reformulate this wave packet, of a free particle. Or in other words, we say that we just redo this Fourier transform of plane waves into the real space. But now we assume that we have two components. We have one component K0. That's positive. Another one has a component minus K0, that's negative. And they have the same energy, right? So that means in principle, eigenstates can be a superposition of these two components, okay? And physically, that is corresponding to two wave packets, one moving from left to the right, one moving from the right to the left, okay? So this is the physical meaning of scattering states, of eigenstate in the continuum, okay? Right, so if you have eigenstate in the continuum, actually, this positive K component represent a wave propagating from left to the right, and the right and the minus negative K component corresponding to the wave packet propagating from right to the left. Okay, so they are limited cases of two different kinds of wave packets. Okay, right. So that is the key point of scattering states or the continuum states. Right. Okay, so let's take a break, and in case it's too fast or you have questions, please feel free to ask. Okay, minus K0, Q minus Q0. Sorry, in the lecture notes I use Q, okay, minus K, but here I use K minus K0. Maybe I messed up a little bit with this notation, so let me check. Let's go back to the. This is K. That's all right, and. Okay, so I'm using K minus K0 in this slides. Okay, in the lecture notes, probably in the printed lecture notes, I probably use the Q minus K. Okay, but you know that that's just only a change of notations. Okay, it's not a big deal. So this is in the K space. This is in the X space. All right. Okay, so now let's consider a slightly more difficult case than the free particle. Okay, let's consider the refraction by just a hard wall. Okay, so that is the case. And this one goes to infinite. Okay, and in this region, so this is x equal to 0, say, and this is v equal to 0. Right? You know that physically, you know that if you have wave packet, okay, so this one goes like this way, okay, at t equals to minus t, much less than -1. And then eventually this one will be reflected back, right, at the t equals to plus t. That's much greater than +1, right? So this is the physics. So if you have a particle just moving from left to right and hit the wall, it will be reflected, right? So the Hamiltonian, of course, it's very simple. So this with just Vx equal to 0 or plus infinity for x less than 0, for x greater than 0. That's very simple. If we want to, you can write down this as okay. I think this is fine. Okay. Right, and then we need to find the eigenstates of this one. So the eigenstates of this one, of course, you know, you can write down the wave function into two regions. Okay, the percent x will equal to say something eigenenergy percent x for x less than 0. But x greater than 0, this must be 0, right? Okay, so this one is region 1, this one is region 2. Okay. Right, so we need to find out what is this one. But on the left hand, it's just free particles, right? The differential equation is very simple. It's just minus h bar squared partial x squared and partial percent squared. So this is annoying. Okay, let me write this one. It's minus h bar squared over 2m d squared over dx squared and percent plus v is 0, right? So 0 times percent, that equals to E times percent, right? For x less than 0. That's very simple, right? So given the energy E, so there's a solution. And this solution, of course, is very simple. It's just plane waves. Times coefficient A and plus coefficient B. Very simple, right? Okay, with K just equals to square root of 2m energy over h bar squared. Okay, so you can say, first of all, for any energy E, there's a solution. Okay, right? So this is form a continuum. So there is a solution for okay, for any E positive, right? Okay, but you need to connect the wave function. Okay, so we need to have again boundary conditions because we have two regions. Okay, of course you should first of all you have the percent you know -0 should equals to percent +0. That's continuous, right? So this gives you one equation. But then in general you should have this one. Okay, so this is continuous differential, right? Okay, but actually it's not needed right here for V equal to infinite. So this one we do not need this one. Okay, so you can see that now we have two coefficients, A and B, one equation at x equal to 0. So that's why, you know, you have a continuum of E. Okay, that means any E is a solution. Actually, this one can be easily meet. right? On the left, you have A, E, I, K, X is 0, right? Plus B, E, I minus I, K times 0. This is the left. On the right, it's just simply 0. So that means you just have A plus B equal to 0, right? Okay. So you can see that this is only one equation, but you have two coefficients. Okay. So you don't have two equations. So that means no matter what is K, there is always a solution. Okay. So this is why you have a continuum for the scattering states, because you have one less boundary condition, or two sometimes, than the case that we have for the discrete state, for the bounded states. For the bounded states, because you require the wave functions goes to 0 at both ends, so you have two actual boundary conditions. So this way, you have to make sure the matrix for the boundary conditions is singular. But for continuous states, because we do not require the wave function goes to 0 at the infinite, so you have fewer equations for the boundary conditions. Okay, so that's why we have a continuum. Okay. All right. So the solution now is very simple. Let's write down this psi E K just equals to A e to I K X minus e to minus I K X. Okay. First of all, this one can be written as simply just I a sine function of Kx, right? So that is actually, you know, they're just standing waves, right? Okay. Okay. So it's so the eigenstates is standing waves. Okay. Because we require the wave function go to 0 at this point. Okay. Right. So then what's the physical meaning? So what is the physical meaning? Okay, let me write down a wave packet. Okay, again. But this one, remember, is correct only for negative x. Okay, so you can actually written as theta x, theta minus x. Sorry. If you want a more, concise formalism, so that will be eikx minus e to minus ikx. Okay, and this is theta function. It's called a, it's some function like this one. This is 0. This is 1. This is x equal to 0. Okay, this is called a Heaviside step function. Okay, right. So that means it's 0 on the left axis. It's a positive 1 on the right axis. But now I put a minus x right here. So that means theta minus x is 0 on the right, and is plus 1 on the left. Okay. All right. So this is the eigenstates we have obtained. Okay. So the question is, what's the physical meaning? We know that this is the eigenstates in the continuum is not physical. It's just a mathematical limiting case of something physical. But what is that? So to understand that, we need to form wave packets. Okay. Let's look at what's the wave packets. Okay. To have wave packets, we need to just form psi xt. That's written as psi ek x e to minus I e k t over h bar, and then you have a wave packet dk over square root of 2 pi, right? Okay, and this one can be written as theta minus x, right? That's something we have we needed to to make sure the wave function is 0 on the right hand side of the axis. And this one you have two components. One is a EIKX per side tiered. This is a time dependent, sorry. Minus IEKT over H bar times per side tiered K. Right, so this is one component. But you have another component, minus. There's also a e to minus IKX minus IEKT over H bar and the per side tiered K. Okay. And we know that to make this one have physical meaning, this one is the wave packet propagating from left to the right with Vg, right? The amplitude is A. And this one is something that propagates from right to left with velocity minus Vg, and the amplitude is minus A, right? Okay, so that is the physical meaning. Looks quite straightforward. So let's look at a different time, okay? So at t much less than so in the beginning, in the past, okay? For t, let me change the color, okay? For t equals to minus t, that's much less than minus 1. Okay, so you have two wave packets. One goes from here to the right with Vg. Amplitude is A. Okay, but you have another one. So this is x equals 0. So you have another one. So this one will be minus Vg. The amplitude will be, how much will be? So it will be minus A, right? Okay, looks fine. But we have forgot this one. We have forgot this theta minus x. So if you times theta minus x, and then this part will, the right hand side will be 0, right? So this without time must, but this one, we actually, only this one will exist. Okay, so this one, if you times theta minus x, it will be just 0, right? So basically, so you have something like a ghost moving from right to the center. Okay, but the real wave packet with amplitude A is moving from left to the right. Okay, and now let's look at the time equals. Let's look at the t equals 0. What will happen? Okay, so now the right moving particle goes like this one. Okay, right. So this is the one that's moving into the right. But remember, you need to times theta x. So actually, only this one is real. And then another wave packet, moving from here. Okay, but only this one is it's real. Okay, so effectively, and then you got a wave packet something like this one. So it's going to be something like this. This one will be cancelled, and then you got something like this. Okay, so you actually have a wave packet that's only on the left. Okay, so what's the physical meaning of this one? This is actually, you have the wave packet now reach the wall. Remember, this is the wall. So there's a wall right here. Right. So the particle on the right actually is possible only when there's no theta minus x. Okay. But if you have this minus theta x, so the wave packet on the right is only fictitious. So you don't really have that one. That's only mathematical. Okay. And then let's look at the case in the far future. Again, you have the wall right here, right? This is x equal to 0. And now this particle will be moving right here with plus Vg going to this direction. And then you have another particle, another wave packet, sorry. That's minus Vg. Okay? Right. So this is the case that t equals to positive t. That's much greater than plus 1. So you can see that what's the meaning of this one? And this one, if you times theta minus x, it will not exist, right? So the right hand side actually you don't need to look at. So the only thing that you have is that you have a particle that's moving in the beginning is moving. You have a wave packet moving from left to the center, and at t equals 0, this one will be refracted at the wall, and then at a much larger time in the future, this wave packet actually will be refracted with the amplitude to be just minus a. So that's a full refraction, right? Right. So because you have a to the, it's incoming from left to right, minus a is the outgoing. This is in the past. This is in the future. Right. So it's an evolving wave packet. Okay. If we don't consider this theta minus x as if you have two wave packets of opposite amplitude, one moving from left to right and one moving from right to the left, and meet at the center, and then you have the wave packet just moving, separate and then move again in the opposite direction. But if you look at the physical cases, you need to consider theta minus x. Actually, there's only one wave packet moving from left to the center, and then refracted by the wall, and then moving from center to the left. Okay. Okay. All right. So you can see that now the physics is become quite simple, right? So now you can actually consider even more general case. Let's consider, for example, refraction by a soft wall. Okay. Now you can see that you have a potential like this one. Okay. Right. So this is V0. This is x equal to 0. This is V equal to 0. Okay. And now you can consider a state with this energy. Okay. I know that in this part you're going to have something like EIKXA plus B minus IKX, right? So this is the left. And on this part you must have something, say C e to minus kappa x, right? And you know that K must equals to 2m E over h bar squared, and kappa equals to square root of V0 minus E to times 2m divided by h bar squared, right? Okay. So in the barrier, it's going to be something, exponential decay goes like this one. Okay. Right. And then have a continuous condition. Okay. So now you have three coefficients. You have A, B, C, three coefficients. You have two equations. So psi minus 0 should equals to psi plus 0. Right. So this gives you an equation that's A plus B equal to C, right? And then you have another equation that's psi prime minus 0 should equals to psi prime plus 0. So this gives another equation. That's going to be IK A minus B should equals to minus kappa times C, right? Okay, 2 equations, 3 coefficients, right? So any functions should be possible. So any energy should be possible, right? So on the right, you got a exponential decay, and on the right it must be something, you know. Okay. Like this one. Inside there's no oscillation, sorry. Okay. So it starts to oscillate like this one. Right. So you can see that it's not a standing wave anymore, but it has some penetration and turning into this one. And again, you should have, you know, from this one, you must have A and B should have some phase shift, right? You will not be perfectly opposite. Okay. So the result will be you can write down the wave function. You can find out the wave function. So I leave that solution to you. Okay. So that will be some kind of A times sine function. Before it's just kx, but now there's a phase shift. Okay. On the right side, just C e to minus the kappa x. Okay. This is for x less than 0. This is for x greater than 0. Okay, so that's the eigenstates. And then you ask the question, what's the physical meaning? Okay, so now you can see that so this part is the plane waves, right? But with that appears only on the left, and this part is only a decaying function, and that will be important only when you consider the wave packets are close to the center. Okay, so then you form the wave packets. Okay, so it will be something like this one. Initially, you have this wave packet, something like this one, that's moving with amplitude A, okay? And then, this is T less than, equal to minus T, sorry, much less than -1. And then this wave packet will actually will come from right here, but now it has some penetration into this one, okay? So this is a wave packet that's oscillating like this one, and this is something like this one, okay? So I have some penetration into the well, okay? This is T close to 0. And then you can see that because of this penetration into the barrier, so you can, it's almost like a, so that means this wave packet can move a little bit into the wall, right? So that means you're gonna have a little bit of phase delay, okay? So you're gonna have, you know, at a later time, this is T equal to plus T, that's much greater than +1. So this is going to be with amplitude, that's still A, but with a phase shift. Okay. So you have a phase shift. So you have the phase shift due to penetration. So because this particle is kind of moving into the wall, so that means its refraction is delayed a little bit. Okay. So that's why you have this phase shift. Okay. So this is the physical meaning of this refraction by a soft wall. Okay. Right. So that's the case for the energy below the barrier. And then you can ask the question, well, what if the energy is above the barrier? What will happen? So if the energy is above the barrier, okay, so now you can have this one will be A E I K X plus B E minus IKX. And this part, you can also have C E I K, say, prime X plus D e to minus IK prime X. Of course, with K just equals to square root of 2m E over h bar squared. And K prime just equals to 2m. Now the energy is different. Okay. You can check that now this one actually satisfies the Schrodinger equation. Okay. And now the boundary condition at x equals to 0. The first one is psi minus 0 must equal to psi plus 0. Okay, so you put x equal to 0 for the two functions. You must have one equation, a plus b equals to c plus d. Right? The second one is that you must have psi prime minus x minus 0 equals to psi prime plus 0. So this gives an equation that's k a minus b equals to k prime a c minus d. Sorry. Okay, so you have two equations, 4 coefficients. Okay, so that means for each E, you have 2 eigenstates. Because now you have 2 independent coefficients, right, to choose. Okay, and so that means you can have different ways to form the eigenstates. You have 2 different ways to form the eigenstates. Okay, and again, we can look at the physical meaning of different ways to do this. Okay, so let's say, suppose you have, let's look at the physical meanings. Of this one. Okay, you look at the wave packets. Let's do the same thing as we have done for Fourier transform. So you can see that this A is going to something incoming, left to right, right? And the B is outgoing from right to the left. And the C is something that's also moving to the right, right? So it's actually outgoing from left to the right because it only shows in the right, right? And the D is something incoming from right to the left. So you can say that that means okay. So if we consider the wave packet at different times, so it's something like this one. Okay, so this is A and this is B. At the t equals to minus t. And in the future, you're going to have 2 wave packets outgoing. This is C and this is D. Okay, and this is the case for t equals to plus t much greater than plus 1. Okay, right. So that's basically you have 2 wave packets coming and then 2 wave packets outgoing. Okay, so you have for refraction. Okay, on both sides. Okay, but now let's consider cases. Suppose initially, so if we consider initial condition, so if we are interested in the case that the wave packet coming from the left. Okay, so we assume that the wave packet is coming from the left, and then in this case we can choose B. Sorry, this is not B. I'm sorry. This is D. This is C. this is C, this is B. I'm sorry. So we should choose D equal to 0. We have this freedom. Remember, we have 2 equations, and then in this case we're going to have 3 equations, 4 coefficients, right? Because you have 1 more equation right here. Okay, and so you still have a solution, and they have a solution that is A, B, C to be determined, right? So now you can see that you have a particle. So A is the particle incoming. Okay, this is incoming amplitude, and then you have a 2. This is a B. That's a. This is C. Okay, so this is refraction, and this is transmission. Okay, so you can see that you can still have if you just set that initially D equal to 0, that means the wave packet coming only from the left. You still find a solution. Okay, if the energy is above this barrier. Okay, so this way you can actually obtain the refraction amplitude and the transmission amplitude. Okay, so that's something we can obtain just by using these conditions. So this is the equation 1, equation 2, and equation 3. Okay, so using 3 equations, and now we have 4 coefficients. You can still find a solution. Okay, always find a solution. Okay, right. So this is the way. Okay, for you to calculate this one. And the physical meaning of this A, B, C, and we see that A is incoming, and B is refraction, and C is transmission. Okay. So now you can write this A is the incoming wave packet amplitude. So B is the refraction amplitude, and C is the transmission amplitude. Okay. For this percent EK, that equals to A E IKX plus B E minus IKX. Right, this is for x less than 0. So we have seen that if you only have this part, A is the incoming part, B is the refraction part, right? You can have another one, EIKX prime. Of course, the wave vector will be different for x greater than 0. So this one is the transmission. So that's the wave packet that's moving from left to right, right? Okay, but now the wave vectors actually will be changed a little bit. Okay, so I give you. Okay, so this is the way to find the solution of this potential. Okay, so this is E. Okay, and K equals to 2me over h bar squared, and K prime equals to 2me minus v0 h bar squared. Okay, now you have all of this one, right? So you have all the coefficients can be determined, okay? Because now you have 2 equations, okay, at the joint point, right? Okay, so A, B, C, and satisfy psi minus 0 equals to psi 0, and psi prime minus 0 equals to psi prime plus 0. Okay, and so this is the boundary conditions, right, at the x equals 0. Right, so you have 2 equations, 3 coefficients, so you are guaranteed to have a solution, okay? Right, and this solution actually is up to a global factor, right? So ABC, because you have 3 coefficients, so you can always choose one to be, say, for example, 1, and you can find this B and C. Okay, so you can say actually the refraction coefficient that can be defined as A divided by B divided by A, and the transmission coefficient. So this is a refraction coefficient. And this one is C divided by A, that is the transmission coefficient. Okay. Right. So now you see a huge difference between the bounded states and the scattering states. Right. So now let me summarize the bounded states and the bounded states. Okay. So the energy EM should be less than the barrier. This is one thing. Okay. Secondly, PHYS should go to 0 at x equal to plus or minus infinity. Okay. So that means the number of equations, the boundary conditions equations, equals the number of coefficients. So this one gives us a discrete solution. Okay. And the bounded states can be normalized. Okay. So they are physical, stationary. Okay. Right. And then for the continuous states, or scattering, okay. So the energy should be above the barrier. Okay. Right. And then we don't need to have this one goes to 0. Okay. We don't need this one. Okay. And then that means the number of boundary condition equations is less than the number of coefficients. Okay. So this leads to solution for any E greater than B0. Okay. So that's why it is continuum. And again, this percent E x is not normalizable. Okay, so that means it's unphysical. Okay, and then you must have a wave packet. Okay, that's a physical, but it's not stationary. So it's non-stationary. It's moving. Okay, it's moving. That's why we call this scattering states, because it's going to either move and reflected, or moving and be transmitted. Okay, or both. Okay, so that's the difference between these boundary states, okay, and the continuous states. Of course, we consider this one-dimensional potentials. Okay, right. Okay, so this is pretty much we have right here. There are more materials in the lecture notes. Okay, so some of them, of course, are a little bit more advanced, and you are encouraged to read them. And if you have questions, you can come back to me to suppose that there are any points in the lecture notes which have not been covered in the lectures, and then you can just come back to me. Okay, so we are not supposed to cover all the contents in the lecture notes, the printed lecture notes. Okay. So, but anyway, let me stop right here and to say if you have any questions.